And question 4. The continuous random variable L represents the error in meters made when a machine cuts poles to a target length. The distribution of L is a continuous uniform distribution over the interval 0 to 0.5. Straight away from here, we can define the uniform distribution. X follows a uniform distribution where the smallest value is 0, the largest is 0.5. We can sketch this situation. 0 to 0.5. And we should also be able to figure out the PDF. The entire area here should equal 1. If the width is a half, the height must be 2. Another way to find that, a more formal way, is that the PDF is going to equal 1 over b minus a. So that's 0.5 minus 0. 1 over 0.5 equals 2. Okay, I'm happy with that diagram, and I should be able to use that to respond to this question. Probability that L is less than 0.4. 0.4 being somewhere close to here. Quick shade. This is the area that I'm looking for. The probability that L is less than 0.4 is going to be represented by that shaded area, which is a rectangle of width 0.4 and of height 2. Probability 0.8. Part B, the expectation of L. Another one marker. The expectation of a continuous random variable will always be the midpoint of A and B, the midpoint of the smallest and the largest values. More formally, it's going to be A plus B divided by 2. 0 plus 0.5 divided by 2, 0.25. Moving on to the variance of L. We once again have a formula for, and the variance is going to equal b minus a squared all over 12. So that's the width of the continuous uniform distribution squared all over 12. 0.5 minus 0 squared all over 12. And in your calculator, you should get the answer of 1 over 48. Okay, so a few small mark recall fluency questions before we move on to something a little bit meatier. So in this part of the question, we were told that a random sample of 30 poles, so there's a big clue right here, 30 poles were cut by this machine. Find the probability that fewer than 4 poles have an error, of more than 0.4 meters from the target length. The fact that I was told there was a sample of 30 poles lets me know I'm working with a binomial distribution, and we're going to set that binomial up. So y will follow a binomial distribution where n equals 30 and p is 0.2. Probability that y is less than 4 can also be written as the probability that y is less than or equal to 3, and this should be in our tables. 0.1227. Great. Moving on to the next part of the question, we're told that a new machine cuts poles to a target length. The error, x meters, is modelled by the cumulative distribution function as shown below. Use this model to find the probability that x is greater than 0.04. Okay, continuous random variables will not give us greater than probabilities. They are only useful to find less than probabilities. So we'll need to do a 1 minus with the stated value. So we need to substitute 0.4 into this function and then do 1 minus that result to get our answer. Substituting that in, I should get 1 minus 4 times my 0.4 minus 4 0.4 squared. Putting that into your calculator, we should get 1 minus 0.96, which leads to 0.04. Okay, so now a random sample of 100 of those poles cut by this machine are taken. Using a suitable approximation, find the probability that at least 8 of the poles have an error of more than 0.4 meters. So, firstly, clues in the question. I now have a sample size of 100 poles. I'm being asked to use an approximation, and the probability that at least 8 have an error of more than 0.4 meters. More than 0.4 is the probability that I just found, that small probability of 0.04, and here n is going to be 100. So y follows a binomial distribution when n is 100 and the probability of success is 0.04. Okay, I've been asked to use an approximation. There are 2 options from the binomial. I can approximate to a Poisson, I can approximate to the normal. Since on this occasion I have a large value of n and a small value of p, that's the perfect criteria for us to approximate to the Poisson distribution. So, I'm going to say, and I'll use a new letter to describe this distribution. We'll go for G. G follows a Poisson distribution of n times p, so that's 100 times 0.04, which is going to give me a lambda value of 4. G follows a Poisson distribution where lambda is 4. So, probability that y is at least 8, so the smallest value of y is going to be 8. After approximating, probability that g is greater than or equal to 8. So this is nice for the tables. I have a value of lambda I know will be in the tables, but I have a greater than probability here. Once again, a 1 minus, and a 1 minus with g less than or equal to 7. Being a discrete distribution, the same value will not appear in these 2 statements. Looking this up in the table, that's 1 minus 0.9489, which gives us 0.0511.